All right. Here we go. Am I recording? I am. Oh, look at that. All right. So here we go. So today we're going to learn a little bit about rotational inertia. Your learning targets are here. There's a lot going on here. So I'm going to let you read through those. And then after the video, you should go back and read them and make sure that you got everything. All right. There you go. So here we go. So far, whoa, that is not at all what I wanted to happen. So far this year, we've learned a bunch of stuff, including the following. We learned Newton's second law, which says that the net force acting on an object is equal to the mass times the acceleration. Now, I know you know this, but it's worth revisiting because we're going to learn all the angular counterparts to this today. We know that mass is a measure of an object's inertia. It's an object's resistance to a change in motion. So the idea is the more inertia, the more mass an object has, the less responsive it will be to a force being applied to it. In other words, if you have more mass for a fixed net force, you'll have less acceleration, right? Okay. And obviously the net force, you know by now, is your total force. And remember that that's what creates the linear acceleration of an object, all right? So we've already learned that torque is kind of the rotational counterpart to force, and we've learned how to calculate that, right, in previous videos. Net torque is the total torque acting on the object, so it's kind of the rotational counterpart to net force. All right, angular acceleration is how quickly your object's angular velocity changes. All right. So it turns out that in the same way that there's a relationship between net force, mass, and acceleration, or I guess more specifically, there's a relationship between the net force on an object and the acceleration. Similarly, there is a relationship between net torque and angular acceleration. All right. So the question becomes, how does an object's net torque determine the angular acceleration? And so to answer that, what we need to do is we need to figure out what is the angular counterpart to inertia? What's the angular counterpart to mass? All right. And the answer to that question is rotational inertia, which is sometimes called moment of inertia. Although I tend to hear that less often. I feel like people are more and more just calling it rotational inertia. But if you hear the word moment of inertia or the phrase moment of inertia, it means the exact same thing. And as I alluded to, rotational inertia is simply the rotational counterpart to inertia or to mass. All right, so in the next video, we're going to focus on this. Newton's second law says net force equals mass times acceleration. So the angular counterpart to that is net torque equals, instead of linear inertia, we want rotational inertia. Instead of linear acceleration, we want angular acceleration. All right, so this is sort of where we're going with all of this. But before we get there, we need to spend some time talking about this rotational inertia piece, all right? And so that's what we're going to focus on in this video here, all right? So in the same way that regular inertia measures an object's resistance to a change in linear motion, rotational inertia measures an object's resistance to a change in angular motion about some axis, okay? So if you want to calculate the rotational inertia of a point particle, here's the equation for the rotational inertia. All right, it's I equals mr squared, where m is the mass of the object, and r is the distance that that object is from your axis of rotation. All right, so let me give you a quick visual on that. All right, so maybe you've got a particle. So here's my particle of mass m. All right, and our goal is we want it to spin around in a circle like this about this kind of central axis here, okay? So the radius of the circle about which our particle is rotating is r, and so to calculate the rotational inertia of this particle about this blue axis, your rotational inertia is equal to the mass that's rotating times the radius of the orbit that it's going to follow squared. Okay, so that is the equation for the rotational inertia of a point particle. Where does that come from, you may ask? Unfortunately, I can't tell you that quite yet. All right, once we get to rotational kinetic energy, I'll give you a little bit more explanation for where that comes from. And in the past, I have done rotational kinetic energy first, and in terms of, you don't care. Anyway, we're doing it later. So there you go, deal with it. So that is how you find the rotational inertia of a particle, and I believe the bottom half of the slide just says what I told you there. Yeah, when we get to rotational kinetic energy, we'll talk a bit more about where that comes from. For now, just note that the inertia depends on both the mass and the radius from the axis of rotation. So here's the big thing then. So the farther a mass is from the axis of rotation, the harder it is to change its angular motion. All right? And you may remember last year we did a demo where we rolled a cube and a disc that both had the same mass down a ramp. And what we discovered was that this one rolled much faster, and this one rolled slower. And the reason was this one has a lot of rotational inertia because more of the mass is farther away from the axis of rotation. Whereas with a solid disk, the mass is kind of evenly distributed, right? And so your mass is closer to the center, and so it has less inertia, okay? And as a result, it's easier to get it rotating, okay? So that's sort of the demo for that. And if you remind me, I will show you that in class. If you don't remind me, if I'm being honest, I will totally forget. So you should remind me. All right. How's that for having a reliable teacher? Okay, so cool. All right, now suppose we've got something that's not just a particle, like a meter stick or a football or something, and we want to find the rotational inertia of that object. Well, to do that, you just add up the rotational of all of the particles. Add up the rotational inertias of all of the particles. So for each of your particles, you do mass times radius squared and add them all up. All right? But with such a large number of particles, it forces us into calculus and becomes an integral. All right? And so we have to take this integral. Now, this equation may look similar. All right? When we learned how to find the position of center of mass, we learned that it was the integral of position dm over the integral of dm. So this equation here, this integral is going to be very similar to one that we've done previously. The only difference is we're using r instead of x, and it's squared, right? So the process is going to be similar. And the other nice thing is there's really only, I don't know, a couple different derivations that you need to know. And then you can just memorize those couple and you'll be good. Or better yet, understand them, all right? So anyway, so all of this, so if you want to find the rotational inertia of an object, you have to take this integral, all right? And so last year in honors, I gave you guys some equation sheets that showed the rotational inertia for different objects, okay? And that's where all of these come from. These equations are all derived using the calculus, all right? And so you're going to be expected to derive, let's see, everything on this page except for, I don't think that they would ever give you this on an AP test. And if they do, then I hate them because those, if I remember right, require double integrals, which feels a little outside of your pay grade. This one is just all of your particles are at radius r, so it's just the sum of all your mr squareds, right? So really, the only ones that require any calculus are these guys, everything in this zone, but some of them are the same, right? Like this one and this one are the same. Because you'll notice that the width of the slab here doesn't come into the equation at all. So here's the one derivation that you need to know. All right. The second derivation you need to know would be this one, which is almost the exact same equation using calculus, or we'll learn another way to do it using the parallel axis theorem. All right. And then the third one you need to know is this guy up here in the corner. And this one is tricky, but once you learn the trick, you're good. All right. So that's kind of what we're going to do here, is we're going to learn how to derive those guys using a couple different techniques, all right? So, here we go. Oh, here's some other ones. Let me see. Yeah, these are all kind of the same, a lot of the same ones. I think the only one that is on this one that's not on the other one, this one is not on the other sheet. Yeah, I guess you ought to be able to derive that one. I never really thought about it. I don't know. I'll look into that. All right. This one's not on that other sheet. I'll have to look into the derivation on that one. And I don't I don't think this one's on the other one either. And again, I'll look into the derivation of that one too. All right. But I know those other ones that I numbered on the previous screen for sure. You got to know those ones. All right. So here we go. All right. So where do those equations come from? Well, as I said, this infinite sum up here becomes this integral. All right. So suppose we've got a meter stick, and we wanted to find the rotational inertia of the meter stick about the center. All right. And in fact, I don't even know why I have a meter stick in here. Basically, what we're going to do is we're going to find the rotational inertia of a rod or stick or something rotating about its central axis, which, if you're keeping score, is this guy, right? Okay. So you can see this one's got it spinning this way. On my drawing over here, I've got it spinning this way, but it's still a rod spinning around an axis that runs through the center of it. Okay? So how do you calculate the rotational inertia of this mess? All right? So in order to do that, it relies on the fact that if you've got a uniform rod or a uniform stick or whatever, it implies that the mass per unit length is constant, right? Because that's what the word uniform means, right? And so what that buys us is we can take the mass of the whole stick and divide it by the length of the whole stick, right? That's the same as if I took a teeny little chunk of mass and divided it by the length of that teeny little chunk. Okay, so this is a very common trick that we can use when we're trying to find the rotational inertia of a thing. Okay, so this is a big useful idea. Okay, so let's see if we can apply that to solve a problem. All right, so we're going to derive the rotational inertia of a thin rod about its center or a plane or slab about its center. Okay. So let's start with that fact. So first of all, again, mass per unit length is constant. So if m is the mass of my rod, capital M, the length of my rod, notice how r is defined here. I hope you guys can see this. I'm just going to let me big in this. Oops. All right, so unfortunately, that made it really blurry. Stupid smartboard. But anyway, what I wanted to point out is r is just half of the length, right? Right, which means that L is 2r, right? Where L is the length of the whole thing. Okay, so when I write mass per unit length, it's the mass of the whole thing divided by the length of the whole thing, right? Okay, and that's the same as if I did this. If I took my rod and broke it up into little chunks of length dr, then if I take the mass of each little chunk and divide it by the size of each little chunk, it buys me that equation. Okay, so that is our starting point for this derivation. All right, and let's move this guy back out of the way. We'll put it back up over here where it belongs with its friend. All right, and you'll notice the plane or slab about its center has the exact same feature, right? Okay, now, so the idea then is our integral, in order to calculate the rotational inertia, so here's the equation for rotational inertia. It's m times r squared, okay? So what I'm going to do, though, is I can't integrate r squared with respect to m. It doesn't make sense, right? So what I'm going to do is I'm going to algebraify this guy to find that dm, and that's little m, is just capital M over 2r dr, okay? Now, technically, this first integral here, we're integrating from 0 until we acquire the total mass of the rod. And now when I do the substitution, because I'm changing dm to dr, bounds of integration are going to change. So r squared is still r squared, and then dm becomes this mess. M over 2r dr. All right, so if you look at the rod, so r, the idea is r is an axis that runs, here, unfortunately I got to pull this back out again. So, bam. So if you imagine an axis running along the length of this thing, this is r equals 0. So here my r is increasing to positive r, and over here r is increasing to negative r. Okay, so now I need to integrate from negative r up to positive r to make sure that I account for all of the mass of the whole rod, right? So if I just went from 0 to r, I would only get half of the rod, which is not what we want. Okay? So, whoosh. Oops. All right. Now, m over 2r is a constant, right? That's just a number. So I'm going to pull that out front. So now I've got this m over 2r times the integral from negative r to positive r of r squared dr. Okay? Oh, well, what's the integral of r squared? That's 1/3 r cubed, right? So this is m over 2r times r cubed over 3 evaluated at negative r and evaluated at r. Okay? And that becomes, well, m over 2r times, so let's see, I gotta do final minus initial. So I'm gonna plug in r, and then I'm gonna plug in negative r and subtract. So I'm gonna get r cubed over 3 minus negative r cubed over 3. So the minus and negative just becomes plus. And so I get m over 2r times r cubed over 3 plus r cubed over 3 is 2r cubed over 3. And look what happens here. Let's see, the 2's cancel out, kabam! And the r's cancel out, leaving me with an r squared. So I'm now left with mr squared over 3, which is the same as 1/3 mr squared. All right, there you go. That's one of our 3 derivations. Okay, so the trick lies in that the change of variables, where you replace your dm with m over 2r dr, okay? So that's kind of the basic premise for most of these integrals. Now, keep in mind, it won't always be m over 2r, but it's going to be something along those lines where you're making some connection between the mass per unit length or the mass per unit area or whatever, and allowing that to give you information about this dm over dr ratio, okay? So you can solve for dm. All right, so that's one of them. Yeah, okay, cool. So, now, suppose we wanted to derive this, all right? So now what we've got is, now we've got a rod, but this time we are integrating it, sorry, our axis of rotation is about the end of the rod instead of through the middle of the rod, right? So now the length is simply just r, right? So now, if you wanted to derive that one, you would do almost the exact same thing, and here are the only changes. When you do your mass per unit length substitution, your dm over dr becomes the mass per unit length, because now r is the length of the whole thing. And when you integrate, instead of integrating from negative r to positive r, you only have to integrate from 0 to r, right? Because you're just going from here out, okay? There's nothing on the sort of on the left side of the axis, all right? Otherwise, the calculation goes exactly the same, and you get 1/3 mr squared again, okay? All right, now, another way that we could, if we wanted to derive this, so again, to be clear, what we did was the first time we had a rod that was rotating this way, and the pivot point was at the center, right? And now what we're doing is we're taking that same rod and pivoting it around at the end, okay? So there's a super secret ninja trick you can do this. If you want to change your axis of rotation, you are sometimes able to use what is called the parallel axis theorem, okay? And so here's how the parallel axis theorem works. All right, so it turns out if you know the rotational inertia of the object, so that's the rotational inertia about the center of mass, okay? In other words, you're having a line running through your center of mass be your axis of rotation. So in this previous example, this guy, if I found I for that, that would give me ICOM, right? Because my axis of rotation is at my center of mass, right? Whereas here, that is not at the center of mass, okay? So the idea is, if we know this, then you can find your rotational inertia about some other pivot point or some other axis, okay? And to do that, use the parallel axis theorem, and here's what it says. It says that the I for your object is equal to the rotational inertia about the center of mass plus mh squared, where h equals the distance from your center of mass to your new axis of rotation. Okay, so for this example here, the distance from here to here would be h, okay, because that's how far my axis of rotation got moved. It got moved from my center of mass over to here to this green dot, okay? Green dot. It's a yummy restaurant if you don't know that. All right, so let's do that. Let's calculate. We know, so here's what we know. So I know this. I know if I have a rod that looks like this, and I call this R, then I know that the rotational inertia about that center of mass is 1/3 mass of the thing times R squared, right? That was the derivation that we did, the big calculus derivation I just did, right? So now the question is, if I call this point down here, if I call that P, what is our rotational inertia about P? So what the parallel axis theorem says is that that is what the parallel axis theorem says is that it is the rotational inertia about the center of mass plus mh squared, where for us, h is that distance, which happens to be equal to r, right? Okay, so what am I going to get? Well, ICOM is 1/3 mr squared plus m, we said h was r, so r squared. And so it gives us 4/3 mr squared, right? But notice how r is defined here. Here, r is just the length of half of it, right? So let's do this. I happen to know that L is the same as 2R, right? So let's take this, move everything down a little so we can see a little bit better. What did I just do? L equals 2R, I just lost track. All right, so this mass right here is the same as 1/3 m times 4R squared, which is the same as 1/3 m times 2R squared, which is the same as 1/3 mL squared, where L is the length of the whole thing, okay? Just like over here, L is the length of the whole thing, so 1/3 mL squared, right? Okay? All right, so that parallel axis theorem is super useful, all right? it is very common to run into problems like this, where they give you some crazy contraption that looks like this. Okay. So here we've got 2 meter sticks that are attached, and they're being rotated about this axis that runs through this, right? Okay. So so if this guy has a length of L, well, we just discovered that I for that is how do I want to do this? Do we want to write it in terms of L or in terms of R? Sorry, I'm totally being wishy-washy here. So here, I guess here's what I'm hesitating on. So this is 1/3 m L squared, which is the same as 4/3 mr squared. It's kind of what we've decided, right? Where r is half of the length, right? Okay, so that's I for the top piece. Okay, so we already know that, all right? Now, we got to find I for this bottom piece. So we've got this meter stick, and it's not rotating about its center of mass. It's rotating about a piece, or about a point that's way up here, right? Okay, so the I for the bottom piece, so I'm going to use the parallel axis theorem again to find this. So it's the same as what I would be if it was rotating about this point, right? So we learned that if this is R, then I can do I, the I about my center of mass plus mh squared. So I about the center of mass is 1/3 mr squared plus m times h. Well, what's h? Either L or 2r, right? Because that's the distance from my actual center of mass to my pivot point, right? So let's call h 2r. So 2r squared, right? Okay, so that's I for the bottom piece. So then the I for the whole piece is the sum of all of these. All right, so the I for this whole crazy meter stick contraption is I of the top, not to be confused with I of the tiger, plus, I thought that joke was very funny. I don't hear any of you laughing. So there's that, and then we got to add on, what is that, 4 mr squared? All right, so 4/3 plus 1/3 is 5/3, which is 1 2/3. Plus 4 is 5 2/3 mr squared. All right. All right. For some reason, I'm not too happy with this one. I'm going to leave it. I want you guys to give me some feedback. Maybe I'll go home and watch it and see if I like it. I know I'm feeling a little off on this one. All right. Well, anyway, there you go. So we've learned 2 things, hopefully. We learned a giant crazy integral that will allow us to find the rotational inertia. And we learned the parallel axis theorem, that the I about some arbitrary pivot point is equal to I about the center of mass plus mh squared, where h is the distance between the center of mass and your new pivot point. All right, I think that's it. It is